welcome to part 3 of this Quant Trading Accelerator. The second part was all about the arrays, and now this is the extending on this. Part 3 is vectorization, which is essentially arrays on steroids. In this video, we're going to build our own data analysis library from scratch while learning all about vectorization. So before we start, we need to do a bit of, vector algebra. Be very comfortable working with vectors. And to do that, I'm going to just copy and paste this vector class. So we're gonna model a vector as a class, and there's going to be some functions here. I recommend that I'd rather go through each one individually because it would be quite a boring video. That if you're interested to know how it's implemented, is then to refer back to the class to see how it's implemented. But it's here for you, and but we'll go back to this class when I'll show you examples. So the first thing we will need to do is specifically to look at is vector scalar algebra. Okay, and so we're going to create a vector using our vector class, and we can pass in an array. And essentially what it's doing under the hood is creating a NumPy array. And it's essentially just a NumPy array with just some convenience like methods for vector algebra and also statistics. And now if I print this out, you see we've got a vector, right? And so a vector scalar algebra is when you take a vector and you add a scalar, and a scalar is just an individual value, so it's not an array. It's just you just call it a scalar. So for example, 1 here is the scalar. So if we add it, and you notice essentially what it's doing is it's looping over the array and adding 1 to it. I mean, so essentially what it's doing is doing this. It's doing 1 plus 1, then 2 plus 1. And 3 plus 1. And you notice it's just more concise. So it'd be really noisy if I just had the notation like this. So it just makes it very concise. So that was addition, right? So we can also do vec minus 2, for example. And again, what it's doing is it's doing 1 minus 2, 2 minus 2, and 3 minus 2. Okay, and you can see that's going to give us exactly the same results. So that's, and it can also be, you could also have it on where the scale is on the left hand side of the operation. And you can also do, for example, multiplication. Okay, and you may be wondering why we're learning this. And the reason is because our data analysis framework is going to be working purely on vectorization. And I'm going to show you the reason why later in terms of performance. So that's, then I'm going to just show you can also divide as well. Okay, so that's and I just want to just show what it's doing actually behind the hood. So for example, we have and this is very important as well. When you're doing these operations, it's creating a new array. So it's not replacing the vector. It's what's called, it's not in place. So it's always creating a new one. So it's essentially, you can treat this as what's called immutable. So for example, this is essentially what it's doing for like the vector addition, right? So for example, so the very first example where we did like plus 1, it's essentially doing this e plus 1 and then phi. And that's essentially the code, right? So you can see just from a visual perspective, it's more concise here and it's very clean, whereas here it's very explicit, and so that's one of the good choices of vector algebra. So now I just want to actually just show you why, I'm going to call this is like a buzzword or marketing of it. Vectorization is the power of vectorization. Okay, so I'm gonna give an example. So for example, this one is going to be 100 million. Okay, we're going to create two vectors or arrays essentially. Well, the first array is going to be for I in range. And essentially, this is creating just an array of ones with a length of 100 million. Then the V2 is going to be our vector. We're going to pass in this Python list into this, and it's going to convert it into a NumPy array for us. So I'm just going to run this. It may take a while. So while this is running, I'm now going to benchmark. So for example, what we're gonna do is we're gonna benchmark that code that we wrote, which is the taking a vector and +1 so vector scalar algebra. And we're gonna do this. We're gonna do for x in v1, y append x +1, and then we're just going to print, because if we don't, we're just going to print out the last 10 elements, because otherwise it'll print out 100 million. So this is what we'll do. Okay, so it's looping over just the Python list, it's adding +1 to it, and then we're just displaying the last 10 elements. Okay, so if I run this, and as it's running, you can see it's going to take it's already taken a few seconds. Okay, so while it's doing that, okay, so now it's 8.3 seconds. Okay, so now we're going to use our class to do exactly the same, and you can see both. So we're going to say y equals, and we've got v2, which is our +1, and then we're just going to do print out the last 10 data points. Okay, and now let's benchmark this, and you can see it's already done in under a second. So so not only is it more cleaner code, but it's also really faster, and this is because it's using vectorization. And so for example, let's just have a look at see the performance gain of it. So we have 8.3. How much is that? 8.3 divided by 4 point, how many second half? So that's 432. So it's just under 20x performance improvement over, and there's two reasons for this. Is because the vector is working with remember we said homogeneous arrays. So because it knows it's always, for example here it's all integers, that it knows that each element is an integer, that it can run specialized CPU instructions to parallelize the calculation. So rather than just do it like one individually, it does it in parallel, just like how GPUs work, where it's all parallelized, but obviously not on a larger scale as GPUs. So that's hopefully you can see this. And so I want to just document this, which is where the speed comes from. And the speed comes from SIMD. So if you're curious to know more about how it does it, then Google this, and you can see some CPU instructions for how it does this. Okay, so now we've done vector scalar. Now we're going to do vector algebra. Okay, so it's very important that the vectors are the same length. If they're not the same length, then you can't do any algebra on them. So for example, we have x here, and x is just going to be a sequence here, and we'll say y equals another vector. And by the way, if you ever use anything like MATLAB, Mathematica, Octave, then this is you'd be comfortable with this. And then -1, 2, and then -2. Okay, and I'm going to just run this. And now we can do exactly the same like operations, arithmetic operations. Okay, so for example, I can do x plus y, and you can see what it's doing behind the hood is this. It's doing 1 plus 1, and it's 2 from x plus this element here -1. So we can just say just make it more explicit though. -1, and then the next is 3 from x, and then the third element on the y is 2, and then the last element in x is 4 plus, oh, that should be, my bad, that should be a plus, and then that's plus -2. Okay, and we should run this and we should get the same code. Okay, so you can see that. And again, you can do all of operations. Okay, so for example, we can do x minus y, and we'll just make it more explicit, like the calculation. So we do 1 minus 1, and then 2 minus 1, and then 3 minus 2, and then 4 minus 2. We run this, and you can see we get exactly the same results. Okay, and let's just do the multiplication. So we do x times y, pardon me. And essentially what it's doing is doing 1 times 1, 2 times -1, because of the, exactly the same we're doing here, and then 3 times 2, 4 times -2. Okay, and I run this. You can see we get exactly the same operations. And now what we're going to do is vectorize statistics. And for example, if you're working with high frequency data sets, it's really important that you calculate very quickly. And so a lot of like for example, creating statistics from your data, it should all be vectorized. So we're going to have a dedicated section to this. So vectorize statistics. So for example, let's say we have log returns. And remember, log returns are essentially just the returns in log space. And we'll go, oops, I put capitals on. Let's just say that for our portfolio, that this is the returns, log returns for our portfolio, and then -0.01, and we're going to calculate the mu, the average, the mean. So and dot mean, and I'm just going to print out the mu, but I just want to show you what it's doing. Like for example, so if we go to the class here, there's a method here called mean. Okay, so essentially it's just calling numpy's mean. We're passing we pass the underlying array, and we pass it into numpy mean. So because the reason we're doing it with numpy is because it vectorizes it, so it'd be really fast. And also, just before, I just wanted to just show you the code for to do the vector algebra, and this is all the code to do it. So for example here, when it was inlined, we used like the plus operator. This is essentially what it was doing. So if you're curious to see how it's implemented, then this is what's called operator overloads. But anyway, we'll go back to our statistics. So that's the mu, right? And then now we can do this. We can actually start calculating statistics from it, vectorized. So for example, we've got the log returns, and we want to see the difference between the log returns and the mu, the average, to see how much they deviate from the average. So you can see here that we've got now the distances, and now what we want to do is we're going to square them. So for example, by squaring them, we're going to turn them all into positive numbers, and the larger the distance from mu, the more it's amplified. So if they're quite far away from the mu, then they're going to be amplified even more away from mu. And the way we're going to do this is we're going to raise to the power, and we're going to raise it by the power of 2. Okay, so that's you can see now what was a negative number is now squared. And this is essentially what's called scientific notation. So it's just a very concise way for writing this. And so now now what we're going to do is we're going to take the average. So what we're going to do is take the average of this, and this is again all vectorized operations. So we're always working with vectors. So for example, now we've got the average squared difference. And now what we're going to do, and essentially this is what's called the variance. So if I print out var, you can see it's exactly the same code here. So it's got these convenient statistic methods to calculate it. So if we have a look at the code here for vectorization, let's have a look. Variance. Okay, so this is, so again we calculate the mu, and then we just we calculate the mean of the squared difference from mu. So that's how it's all calculated. You can see here we're not using any loops here whatsoever. So this is so you get 2 wins here. You get that it's you can write more concise code, and it also allows you get a huge performance gain from it. And this is really, vectorization is like very important for working with high frequency data sets. And now what we're going to do is we're going to do this. We're going to take the square root, and when you take the square root of and we're going to just do the variance here. So for example, we're going to take this here, okay, so that's the what's called the standard deviation. This is the math for it, but obviously I've made it convenient. And then for example, it's essentially this is square root is log returns variance. You can see it's exactly the same number, but we don't need to. We can also just call STD, not sexually transmitted disease, standard deviation. This now we call this. it will give you exactly the same value. So it's just a convenience method. And we have a look at, again, we're going to have a look at the calculation for this. And you can see there's no special voodoo magic here. It's just purely vectorized calculations. So for example, we calculate the variance vectorized, and then just take the square root of that, and then that gives us our standard deviation for the vector. So that's how we can do, for example, we could work with like large data sets and calculate the statistics very quickly because of this vectorization. And just because we've just mentioned mu and also the standard deviation, I can now introduce some financial applications. So we can do the vectorized version of the Sharpe ratio. So vectorized Sharpe ratio. So the vectorized, so let's just have a look at, let's just say I've got some portfolio log returns, okay? And I'm just gonna 0.01. So let's just say that the returns, this is the returns on our portfolio. So it went up by 1% in log space, and again 1%, and then let me just do 0.2 minus 0.01. Okay, remember with log returns, they have this property called time additivity, and the time additivity allows you to sum the log returns up. So for example, this is our total compound growth rate for our portfolio. So you can see it's 3%. And we can also calculate the mu for it very quickly. It's just the mean. Oops. We can calculate the mean, and we can also calculate the standard deviation. So then we can see the standard deviation. Okay, so essentially the Sharpe, the basic version of Sharpe, is you take the mean, and there's actually with the Sharpe you have this thing what's called the risk-free. You have to factor in the risk-free rate, but in high frequency trading and quant trading, was where it's usually intraday trading, you don't factor in the risk-free rate because you don't hold it long enough to accrue any risk-free rate. So, and essentially this is mu over the standard deviation. So this is quantifies what's called risk-adjusted returns. So the higher the number, the more risk we're reducing, like returns, like how stable the returns are essentially. So for example here, this is 0.68, but I think it'll be more concrete if I show you another example. So it's going to be a portfolio which has the sum of a same compound rate of 3%, but it's going to be less stable. Okay, so let's just, so I'm now just going to choose, now we're going to do portfolio log returns. I'm just going to override to give you some new ones. So we're going to say 0.1%. So in this time series, it goes down 3 times by 1%. And then on the last time step, it's going to go up by 6. Okay. And if we have a look, portfolio log returns dot sum, we look at the sum, that it gives us the same compound growth rate of 3%, but obviously this standard deviation will be much higher. So the standard deviation is just a measure of how much it deviates from the mean. So you can see here that we'll calculate the mean again, and the mean should be the same. So exactly the same mean, but we're going to see here that the standard deviation is a lot higher. So if we look at the standard deviation, you can see now like it's nearly 3 times larger than this one. So now if we calculate the sharp for this, and also as well, usually what you do something called annualize the sharp rate, but I'm not doing this for just this basic example. So you can see here that, so let me just reiterate that the sharp ratio, the higher the number, the more stable the returns are. So, and even just like empirically, if we have a look at both of these, like if I gave you these 2 portfolios, which one would you choose? You would choose this one because it's it doesn't have hardly, it just has one small drawdown, right? Whereas here it has like a quite a big drawdown, and it goes up by, let's say, 6% higher drawdown. So drawdown is like when your equity, you go into, say, negative equity. But we'll discuss this later. But but you can just see, just intuitively, we can, like, this is more stable returns. Like this is majority negative, and there's like a huge big price increase. So if we were going to choose like to invest in what either portfolio, you would choose this one. So, and essentially it's just quantifying this. So now we've introduced like a vectorized sharp calculation, and now we can actually start building our own data analysis library. So I'm going to add a new section, build a data analysis library. So this is, I'm throwing you in the deep end here, but I strongly believe like you have really, if you build things from first principles, that you really understand how pandas and polars really work. So again, we're not going to go, it'll be incredibly boring to go over all this code, but if I use a certain function, and I really recommend to looking to see how it's implemented. And now we've got a column, and essentially it's just, let me just make it clear what it's doing as well. So it's essentially just a wrapper over our vector class, and it also you have to provide like a name, a string, and it's essentially it's all the same calculations. And now we can create a column like this. So for example, we could create a column here called trade P&L. And let's just say these are, so the P&L is your profit and loss. Let's just say we have 4 trades. First trade made $2. Then the second trade lost $1. And the third trade won $3. And then the fourth one won $1.50. Okay, and we can just print this out, and you can see here it provides us the name of the column and also the underlying data, and the data is essentially this NumPy array. And essentially we want to model several columns and put them all together as a table. But we're going to just rather than call it a table, we're going to keep to the same nomenclature of pandas and polars. So they call it a data frame. So we're going to also call it a data frame. And I'm going to just, out of magic, I'm going to just copy and paste this code here. And again, I'm not going to go over each code individually, but I really just recommend is if you see a code example and you're curious to know how it works, then to find the method and to see how it's actually implemented. So now what we can do is we can actually start to build tables. And so for example, I'm just going to import, we're going to use like date times. I'm going to get time delta. And so, for example, if you want to use like a library either through the Python SDK or the like any third-party library. So, for example, when we go into the machine learning, we're going to use some third-party libraries. This is how you import your libraries. So, just this, essentially, we're importing these functions from this datetime module. So we're going to first column, we're going to create a column. I'm going to call it time. Oops. And we're going to create what's called a loop comprehension. And it's essentially just like an inline array. So for example, we're going to start from the 1st of October. And we're going to use this time delta, and we're going to say that days equals I plus 1 for I in range of, we're going to just do 7 here. Okay, and now we're going to create our second column, and our second column is going to be price, and I'm just going to just copy and paste some numbers. I'm just going to save time, I'll just paste them here. Okay, so that's our columns, and now we're going to create a table or data frame to be more exact. And so time and price we pass in, and we're going to just print it out. So you can see here, and this is essentially what Pandas is doing. It's very similar. There's like just a bit of a difference in how the memory structure, but it's very similar to this. So this is what's called like a column order data frame. But I'll go into the difference between column order and row order, which comes from linear algebra. But you can see here, this is the table. And so one of the things we're interested in doing of a very common functionality is to shift. And when you shift the data, for example, because our machine learning model, just any model that we're going to use, for example, we want to predict, let's say, the future price, maybe from the previous price. So this is what's called like auto regression. And so what we're going to do is just take the price lag 1 and its shift, and then we're going to print out price lag 1. So you can see here it's shifted the values. So for example, this was on the first element, now it's the second element, and because obviously there's no previous element, then it just represents it as an NaN. So I recommend to have a look at the code how it does this. So that's the code, and now what we can do is we can append this. So we can do table append price lag 1. Because I didn't wrap it into as a column. Okay, so then we're going to call it price lag 1. Okay, so now we will print out the table. So now you see we've got like 3 columns now. Got the price and price lag 1, and you can see like on the same row you can see that what the previous price is. So when we pass this into like a machine learning model, we have to get it in what's called row order form or row major. So essentially what we're not going to use price, and there's several econometric reasons why we shouldn't use price, but we'll maybe discuss this in a future video when we go into more the econometrics. But so for example, we can try and predict the price based on the lag, the previous price. but we're going to look into the log return instead of the price, and that's what we're going to do now. So we're going to take the price, and we're going to do division price lag 1. Okay, and this is essentially just the ratio between the price and the price lag 1. So it's literally taking this number and dividing it by this number for each element. Okay, but we can also write it like this as well, because we've done what's called this is what's called operator overload, and this corresponds to, let me just show you specifically where have I done this? Oh yeah, sorry, this is in column. So here we go to true div. Essentially this we overload this operator, so we can do this. And so that's exactly the same calculation, but just using operator overload. And so now what we can do is we're going to now create a new column. Essentially what we want to do is build log returns. And first what we need to do is calculate the ratio. And then we're going to create a column out of it. So I'm going to call column ratio. And we're going to append it to the ratio col. And then we're going to just print it out so we can see here the ratio. So we're just dividing price divided by the price lag 1, and that gives us the ratio, right? So we're halfway there to calculating the log returns. And to create the log returns, now we're going to now we need to create a new, make this more explicit. So we'll say generate auto regressive log returns. And with our models, we want to predict the future log return from the previous log returns. So the premise is that there may be some predictability looking at previous log returns to predict the future log return. So we're going to create log returns, and to create log returns we can just take the ratio column and call the logarithm. So we're just going to take the logarithm of the ratio. Oh, I just want to call that log return, and I'm just going to print it out. So this is our log returns, and again what we're going to do is make a column out of it. I'm going to call it log return. Okay, and then we're going to append it to the table. And then table. Okay, so now it looks quite busy now. So I just added the ratio just to make it very clear, like the natural progression of how we calculate the log returns. And imagine, right, this was like 100 million data points. We can do this calculation very, very quickly, which is because it's vectorized. So this is like how essentially professionals do data analysis. They make sure that all the calculations are vectorized. So now we've calculated the log returns. Now what we want to do is, because it's going to be autoregressive, is we want to model the first lag. So for example, we're going to do this. We're going to log return lag 1 column. I'm going to create a new column, log return lag 1 then log return col, and we're going to use the shift. So just like we did with the price lag, we're going to do exactly the same, but with just log returns. And then we're going to, again, we need to append it. So it's going to add it to the end of the table. And then we're going to print it out. So our data is now ready to do forecasting or predictions now. So this is what's called an autoregressive model, because what we're going to do is we're going to predict this. This is what's called the target. This is what we want to predict based off this. In traditional statistics, this would be the independent variable, but in machine learning we call it target, and this is our feature, or the dependent variable. Independent variable. So we're going to, essentially we want to, from this number, we want to predict the log return for each row. So that's, we're all pretty much got everything all ready to start on the next video, which is to do predictions, forecasting. But before we go into, there's just a very important, because at the moment I just need to go into about matrices, and maybe so in the next video we'll go into more forecast and prediction. But to do this, we need to get comfortable with matrices, and so I'm just going to I'll just need to introduce column order, the difference between column order and row order. So for example, or column major order, column major. So in linear algebra they call it column major, but let me just start it here. So for example, a column order is, for example, is essentially how we're structuring our data at the moment is column order. So for example, like this, and then the matrix is like this. So then MP array X minus Y. Okay, and then if I print this out, you can see here that now if we take the first element, it's the first column. If we take the element here, it's the second column. Okay, so but majority of machine learning libraries expect it to be in what's called row order or row major. And row major is exactly the same data, but it's just structured completely different. Well, not completely different, but just in a different order. And this is what's called row major. Okay, so I'm just going to now show how it's represented, how it should be represented when we pass it into machine learning libraries. So for example, we're going to, this is exactly the same data, but we're just now, this is what's going to be called row major. So we're going to combine them, each row, essentially it's like a row level. So now I'm just going to add them here for 1. But now when we take the first, rather than being a column vector, it's going to be a row vector. So this pertains to the first row. Then we look at the matrix 2, the second row, and you can see that I just might as well just do it for the rest. So matrix 2, matrix 3, and that's the last one. So because, for example, this is like we're going to pass them into our machine learning library, and it needs to know, like for example, the features for each row. So it's important that we put things in row order, And I'm just going to make this more explicit now. So for example, how can we create features? So that's what we're going to do now. And to create the features, I've created a functionality to extract the. So for example, we've got so we denote the model input as X, and we're here. What we're doing is now we're passing this in, and this is going to. I've made it this. Again, this is what's called operator overloading. And now it's going to put it in row order. So for example, now you can see here, but in practice, you'd remove this NaN. There are some machine learning models that it's fine with handling nulls. For example, gradient boosting trees, they're perfectly fine to work with, like nulls essentially, but in practice we would drop these before running this for training a model. So that's our features, and we denote them by X, and you can see here it's row order. So for example, we had some more lags, and actually that's going to be one of the exercises is going to be to create lags. So that's the X, and now we need to create the target. And to create the target, we can say we denote the target as Y, and this is what we want to predict. So for example, the table here, and what we want to predict is the log return. And if I just print this out, and you can see here, this is the log return. So essentially, we from X, we want to predict Y. So essentially, we're all really good now to start actually building a model. So now we're going to go into the exercises. The first exercise is to create log returns. So I want you to have a go at doing this yourself. So I'm just going to copy and paste this because it'll be quicker. Let me just. Okay, so here's a price time series, and I want you to create log returns. And so if I just run this now, you can see here that's the data, and then I want you to implement it here. And I want you to make sure that it's vectorized, and you can do it as a one-liner. So I did it very painfully, like from the ratio, whereas I would like you to do it just like in one line of in a one-liner. So that means like in one line of code. And then just to make sure that you're calculating it correctly, then it should pass this test here. And essentially, because we're working with floating point numbers, that for example, you may not get the exact floating point number because there's lots of imprecision in floating point numbers, but we want it to be close to a certain, what's called an epsilon, like a very small number. And this just allows us to do it. And so, for example, we want to just make sure it's the last column that we're interested in, and to say like it should, this is the math, it should be calculated, and it should be this should equal true. So that's the first exercise. And now the second exercise is to do this. Exercise 2, add log return lag. And the lag, remember, is the previous log return, like the previous value in the time series. And you're going to add the code here. So add log return lag column. Okay. And to make sure that it's calculated correctly, that's what it should equal. Okay. And now the third one is going to be quite tricky. So this is way more advanced. So it's really, remember I was saying that we want to remove the nulls, the NANs and the nuns from the data set of vectorized filter. So we want to filter the data out, but we need to do it in a high performance manner. So we want it to be what's called vectorized filter. So we don't want to write any manual loops to filter the data. So what we're going to do here is do x equals np array. And this is the data, right? So this is very common, like especially if we're creating lags and log returns, is that we're going to get a time, like a vector where the first elements are NANs. So for example, 0.1 minus 0.2, 0.2 minus 0.1. And essentially what I want you to do is we're going to implement a method. I haven't really introduced methods, but essentially a function or method is just you have an input and you implement some code and you can return an output. So and at the moment I'm just going to return, this is completely wrong and it's not going to drop the data. So for example, but I want it to drop the data. So I want it to do, so if I drop NAN and I pass the data in, it should equal this. Actually, maybe we'll do this in, we're not going to do this one. So we'll do this another time. So that's the end of the video. So the next part is we'll actually start looking at the model now. We'll look at what's called a closed form model. So it's not machine learning, but it's, well, yeah, you can call it machine learning. We're just going to build a basic, what's called an autoregressive one. Maybe if I write it down here. So the first thing it comes from econometrics, is we're going to build an AR1 model. So that's the next part. Okay, thank you very much. This course is free thanks to my paying Patreon supporters. If you're getting value from this series and want to help me create more, please consider joining them on Patreon. You can also support me by buying me a coffee on buymeacoffee.com. Links on my channel details page.